गुड मॉर्निंग फ्रेंड्स। आज हम कॉम्प्लीमेंटेशन टेस्ट के बारे में डिस्कस करेंगे। अगर इसकी इम्पोर्टेंस देखी जाए तो CSIR नेट एग्जामिनेशंस में, गेट एग्जामिनेशंस में और यूनिवर्सिटी एग्जामिनेशंस में यहाँ से अच्छी भली तादाद में क्वेश्चंस पूछे जाते हैं। ये एक समझने वाली प्रोसेस है। इस टेस्ट के थ्रू हम एक क्रॉस जनरेट करेंगे और उस क्रॉस के जो रिजल्ट्स होंगे उनसे हम ये इंटरप्रेट करेंगे कि होने वाले जो म्यूटेशंस हैं जो एक ही इम्पैक्ट दिखा रहे हैं वो एक ही जीन को ट्रबल कर रहे हैं या डिफरेंट जीन्स को ट्रबल कर रहे हैं। फिर हम उनके लिमिटेशंस के बारे में बात करेंगे कि कहाँ कहाँ कॉम्प्लीमेंटेशन टेस्ट काम में आ सकता है और किन केसेस में ये काम में नहीं आ सकता। सो लेट्स बिगिन। द फर्स्ट एंड फॉरमोस्ट थिंग इज कि जब हम किसी जीन के बारे में, जीन के फंक्शन के बारे में जानना चाहते हैं तो क्लासिकल जेनेटिक्स के दौर से ही म्यूटेशंस की स्टडी हुई और म्यूटेशंस के थ्रू ये तय किया गया कि कौन से जीन का क्या फंक्शन है। फॉर एग्जांपल, जीन ए कोई पिगमेंट बना रहा है, साइंटिस्ट ने उसको म्यूटेट कर दिया। म्यूटेट करने के बाद में अगर पिगमेंट नहीं बन रहा है तो डेफिनेटली जीन वन ही पिगमेंट बना रहा था। सो सच काइंड ऑफ रिलेशनशिप बिटवीन द phenotype and the gene have been studied in the history of science through mutations, and these mutants identified by phenotype from the different wild type. So mutations have the primary role in determining the function of the gene. So when the scientists were very busy in the mutational studies, they found multiple mutants are there, and these mutants are having the similar kind of phenotype. So there was a need to differentiate that which mutations belong to which gene. That's why there was the necessity of the discovery of complementation test. Complementation test is historically known as the cis-trans test, but here there are the two categories, cis test and the trans test. Cis test doesn't tell us anything, but it can be used as a control for the trans test. Now, the trans test is the actual complementation test, and this complementation test determine whether the mutations, two or more mutations, which are quite independent for and generating the same phenotype, do they belong to the same gene or the different gene? If they belong to the same gene, they are called allelic, and if they belong different genes, they are called non-allelic. So what it mean? Complementation test हमें ये बताता है कि एक से ज़्यादा म्यूटेशंस जो एक ही फिनोटाइप जनरेट करते हैं, क्या वो एक ही जीन से बिलोंग करते हैं या वो म्यूटेशंस अलग अलग जीन्स में हुए हैं। इसका मतलब है क्या वो म्यूटेशंस एलिलिक हैं या तो वो नॉन एलिलिक है। कॉम्प्लीमेंटेशन टेस्ट को प्रूव करने के लिए या परफॉर्म करने के लिए हमें क्रॉसिंग की ज़रूरत पड़ती है, जो हम अगले सेक्शंस में देखेंगे। अगर म्यूटेशंस अलग अलग जीन में होते हैं तो फिनोटाइप क्रॉस करने के बाद जो फिनोटाइप डेवलप होगा वो वाइल्ड टाइप का होगा। इसका मतलब कॉम्प्लीमेंटेशन हुआ है। एक डिप्लॉयड ऑर्गेनिज्म की एक कॉपी एक इंडिविजुअल में थी, सही थी, और दूसरी म्यूटेंट थी। दूसरे इंडिविजुअल में जो क्रॉसिंग में पार्टनर है उसमें पहली कॉपी म्यूटेंट है और दूसरी कॉपी नॉर्मल है। दैट मीन्स देयर वुड बी द रीस्टोरेशन ऑफ फंक्शन by the normal copies in the diploid organism that comes together in the next generation after the cross. Similarly, if the mutations, that means more than two mutations having the same phenotype, If the mutations are in the same gene, the generated phenotype after the cross will be a mutant because there would be no chance of the complementation. So in this diagram we can see here there are the two sets. One is A and the another one is B. In B, firstly we are going to consider where there is no complementation. There is a single gene. There are two parents, they are being crossed and the progeny is generated. Now, in those parents, the mutation is occurring in the trans situation. That means that is happening in both the homologous copies of a single gene. That means they are occurring in both the alleles of the same gene. And same situation happens with the other parent. Now, if we consider both of these parents, we found that no allele is the normal allele. That's why they are mutant, because they cannot produce the normal copy of a protein. When these two are crossed and the mutant allele of parent 1 and parent 2 come together, still because they are not producing the normal protein copy or the functional product, that's why they cannot perform and the progeny would remain mutant. So what we have considered, if mutations are in the same gene, phenotype will be mutant. That means no complementation. So here in this diagram, in B diagram, we have seen that there is no complementation. That's why the mutant phenotype is generated. On the contrary, part A or set A of this diagram, that basically tells us the complementation. For the complementation, we require cross and we have to see the impact in more than one gene. For example, in this parent, in parent 1, you can say gene 1 is mutated. In parent 2, gene 2 is mutated. That means what? That means in parent 1, gene 2 is normal and in parent gene 1 is normal. So the normal gene comes from both these parents and they are being restored. That means they are complementing each other. Their normal copies are complementing with each other. That's why they are producing the wild phenotype. For example, from the parent 1, gene 1 is defective, but from the parent 2, gene 1 is normal. So here parent 2's gene 1 is functioning and in this case parent 1's gene 2 is functioning. So one parent is complementing to the other parent, or in this simple situation we can say one allele is complementing to the other allele. Now we can easily interpret few things. Firstly, we need to consider that if the trans heterozygote show mutant phenotype, then the mutations are located in the same gene. That means the mutations are allelic. Such mutations are grouped into complementation tests. This is the case of B. If a trans heterozygote is mutant, then definitely the mutation is occurring in the same gene. That means if we are moving from the progeny towards the parents, considering the phenotypic studies, then in the phenotype we can only find out whether the phenotype is mutant or the wild type. So we are getting the result that the trans heterozygote is mutant. That means the two copies coming in this trans heterozygote are both mutant. That means these two mutations do belong to the same gene. And if the mutations belong to the same gene, they are put together in a common complementation group. Now the second situation. Again, we need to consider this diagram. If the trans heterozygote, that means this progeny, is a wild type, then we can infer that the occurring mutations do belong to different genes. If we see the parent, we can find it out that the mutations in one parent belong to gene 1 and in another parent belong to gene 2. So, such kind of mutations are grouped into different complementation tests. Okay, that means if somebody asks us that how many complementation group are there, then we need to find out that how many genes are affected by the mutations in the simple language. That means mutations do belong to different genes. That means there are more than one complementation group. In a simple language, non-allelic mutations represent a different complementation group. So friends, we can find out by means of this complementation test that how many number of the genes are there for the mutations with the same phenotype. That means mutations, those are producing the same kind of phenotype, are occurring within the same gene or in the different gene. It was the original operational definition of the gene that has been provided by the complementation test, that mutations in the alleles of a single gene do not complement, while those located in different genes show complementation. So this is the underlined statement. In a single statement, the crux of the whole story comes into is the mutations in the alleles of a single gene do not complement, while those located in different genes show complementation. If mutations are occurring in the same gene, do not complement. If the mutations occurring in the different genes do complement. This is the basis of complementation test. We can find it out by the different example. For example, we are having the Drosophila. There are two kinds of Drosophila, we can say. One is the wild type and another one is a mutant. The wild type is having the gray yellow color. Okay, and the mutant are having the black color. We took two black colored Drosophila and we generated a cross between them and they produced wild type. That means definitely the mutant parents do not have the mutations in the same gene. So we can see here again, here the E gene is mutated and in the another parent the B gene is mutated. One copy of E gene comes here and one normal copy of B gene comes to the progeny, and that's why complementation occurs and the normal progeny by means of the mutated parents can be generated. So this was regarding the complementation test, but we need to know that complementation test is not applicable for any kind of mutations. After some time, many of the categorization of mutation have been studied, and it was found that the mutations which are recessive and non-polar in nature, they only can produce the complementation test. That means complementation test cannot be applicable for the dominant mutations. What's the meaning of dominant mutations? Those mutations which show their derogatory or detrimental impact even in the presence of another wild type allele. What is the recessive mutation? Recessive mutations are those which alone in a single copy cannot produce their impact, or we can say in the presence of wild allele, a recessive mutant allele cannot show its impact. So dominant mutations, since they mask the impact of the wild type allele, that's why they don't allow complementation. Similarly, For the polar mutations, complementation test is not allowed, because in polar mutations, what happens, the impact of the mutation carry for the other genes which are located downstream of that mutations. So more than one gene are basically hampered because of such kind of mutations. So this is the overall situation of the complementation test. So complementation test can be applicable only for the recessive and non-polar mutations. Thank you so much. Stay home, stay blessed.